So good morning. It's my true pleasure to be here to present the status of the ALMA project. And I would like to deeply thank the organizer to give me the opportunity to present this talk. So I haven't put any name here because I believe that the whole staff of the observatory and everybody who has contributed to the ALMA project should be listed, which is too long, but I will do that at the end of my talk. This is an image of the ALMA project taken by an airplane. It is a beautiful image, but it also shows you the uniqueness of the ALMA project, both in terms of its scope, the number of antennas, but also in terms of the landscape in which it is located, which is indeed a unique landscape in the northern part of Chile in the Atacama Desert. The area is called the Llano de Chasnantor, which means in the old Kunza language of the Atacameños, the land of departure, which I think is a nice concept for an observatory. ALMA is an array of 66 antennas, which is using the aperture synthesis technique and functions as a zoom array over the entire accessible submillimeter spectrum up to the 1 terahertz domain. It's located at 5,000 meters, so it's one of the most advanced technological observatory ever built on Earth, and it's about halfway through space. It can go from a very compact configuration where the antennas are about in a circle of about 200 meters or so, up to a very extended one where the idea is to extend the antennas up to 16 kilometers. It's operated remotely from a station which is at 3,000 meters called the OSF down in the desert. And the idea is to have it operating for more than 30 years. So why the Atacama Altiplano? Where to go in this remote place? As you know, the millimeter, submillimeter frequencies are essentially blocked by the atmosphere, and you have to go to high sites to diminish the content of water vapor. So you have to be very high and very dry. And also you have to have a plateau which is extended enough to extend the antennas to achieve very high angular resolutions. There are not many places on Earth where you can do that, and this is one of them. The other one is clearly the South Pole for logistical reasons. The Chilean location was preferred. So this is an image of the site before any antenna was moved on, and this is an image which was taken last week by Extracopter, a drone helicopter, where you see all the antennas on the site. It was taken during the last arrival of the 66 antenna on the site on Friday the 13th of June. So it is a global project. It's an international facility with a partnership which includes Europe through ESO, North America, that's United States and Canada, and East Asia in cooperation with the Republic of Chile. The mission statement of the joint ALMA Observatory is to collect and deliver high-quality data sets to the scientific community by operating and maintaining a state-of-the-art observatory to explore the universe in the millimeter, submillimeter wavelengths range. And to this effect, the joint ALMA Observatory will provide a stable operating interferometer, maximize the availability of the array at all times. Oops. Could you switch to the next slide, please? Thank you. This is a view of the Operational Support Facility, the OSF, where most of the work is done, in particular the technical building, which you see in the middle of the image here. Which is noticeable is to the right you have the bases where the antennas have been assembled and built by the three consortia, the European, the East Asian, and the North American one. The people working at the observatory are living in the camp, which is to the left part of this image. The technologies that enable ALMA are complex, and the main aim here is to achieve a very high sensitivity and also high angular resolution. To achieve those goals, you need to go to many different parts of the array, be it the antennas, the receivers, the correlator, and of course also everything which has to do with the signal processing. I don't want you to read that slide, but it just gives you an idea about the complexity of such an array called ALMA. Of course, all that is only working if the spectrum is clean, and it's one of our tasks, and we're working here very closely with the relevant people to make sure that the spectrum coverage in the Atacama region remains clean to enable us to capture the very weak signals from the celestial sources. To give you one example of the technology, those are the antennas. As you know, there are 3 different antenna manufacturers and 4 different antenna types. There's a North American, which delivered 25 12 meters antennas. The European also delivered 25 12 meters antennas. And East Asia delivered 4 12-meter antennas, which will do total power, and an array of 12 7-meters antennas to do the low spatial frequencies. The antennas have extremely precise surface accuracies, about 12 micron or so, better than 12 micron, and all the specifications of the antenna, although the manufacturers are different, are compatible. The equipment and the data flow between the ALMA centers is illustrated in this slide. So you see it's a back and forth between the northern hemisphere regions, Asia, Europe, and North America, and Chile. And it goes back and forth, because if there's a very difficult maintenance to be done on one of the elements of the array, then it goes back to the center which delivered it. To its way to the ALMA site, it has exotic encounters, like here. This is a piece of an antenna going to the site. And then once it's built and assembled on the site, then it is delivered to the high site with a specialized truck. There are 2 of them. And this is an image of last June 13th, delivering the last 66 antenna to the high site. In that sense, it's a huge milestone, because it's the end of the antenna integration verification, which was a main task of the whole project. And as a fact, it really sets the end of one of the major tasks of the construction. What is the current ALMA status? The construction project is essentially finished. The official date of the end of the construction is September 2014. And although the construction will end, there are still a number of remaining items and commissioning items which have to be finished, which include the band 4, 8, and 10, and also the antenna pads and the long baselines. I will come back to that later. Today, all the 66 antennas have been accepted, and currently there are 64 antennas on the site which are available for science, of which 47 on average, between 44 and 54, are being used for the current cycle of observations. The compact Atacama array, or the Morita San array, so the 12 7-meter antennas and 4 12-meter antennas, has been accepted and is currently used for the ongoing cycle 2 observations. Concerning the ALMA observations, the current status, as I said, there are 64 antennas and 54 are the maximum I use for science. In terms of receivers, there are the 4 baseline bands at 3 millimeter, 1 millimeter, 850 micron, and 450 micron, which are installed on all of the antennas and which are available for science. And now there are receiving bands which are partially installed. The 2 first at 2 millimeter and 650 micron, so the 4 and 8 band, are installed about 2/3 of the antennas. And then the very high frequency band 10 at 350 microns is installed about half of the antennas and available as well. The longest baseline which has been used in science verifications is 3 kilometers for the time being, and I will show you an example of results which were obtained with this long baseline. But the plan is to test in the end of 2014 the very long baselines up to 12 kilometers, with the goal to have those commissioned and tested and implemented in the cycle 3 observation run, which will start in 2015. So those are the bands and the atmospheric transmission I just mentioned. In red are the ones which are installed on all the antennas, and blue are partially installed. And the ones which are not framed are the ones which are still being either worked on or produced and will ultimately be part of the ALMA array. The cycle 2, as you know, started on June the 1st in time, and I think successfully so, with a much better operating and much more efficient array than in the past. It's also a much more stable array, which is now not suffering anymore from the many power outages that we had in 2013. We initiated a remote restart of the antennas, which saves us a lot of time and allows us to have a smooth operation. For cycle 2, 1,384 proposals were received. I think it's the largest number of proposals ever received by any observatory. And out of them, 353 A and B rated proposals were selected, and 159 C rated proposals. So those are ongoing now. For the cycle 2, there promised 34 12-meter antennas, and then the ACA. For the receiver bands 3, 4, 6, 7, 8, and 9, with the provisions I said before. And the highest resolution will be 0.08 arc seconds with the longest baseline 1.5 kilometers. And note that there is a carryover from cycle 1 because we had all these problems last year with cycle 1, including in last May with baseline pads. And there's about a carryover of about 460 hours. ALMA is, of course, not a static instrument. It will evolve, and there are development programs ongoing. And here's a list of the programs. I won't read everything here, but there are bands, new bands which will be installed, bands which will be improved, like the band 3. There's an increased flexibility through the addition of a 6th subarray. And also there are software developments which will improve the access of the data and the manipulation of the data. Finally, there's also an optical fiber project which will be closed at the end of the year and which allow a very fast connection between the OSF and Santiago. So there's a robust development program which is going on, and this will really allow for ALMA in the next coming decades to continue to do transformational science. Let me just show this slide to show that there are other presentations during this week about ALMA, and at least here the major ones I picked up from the abstract book. The data and publication, we are doing pretty well. There are about 100 papers which have been published so far based on ALMA data, and you see here the distribution compared with the VLT and the HST. You see that we're doing pretty well here. And which is remarkable is that about 10% of the publications are published either in Nature or in Science. I should have started with this, but the interest of doing studies at millimeter, submillimeter frequencies is essentially to probe what is called the very cold universe. This is an image not of ALMA, but of IRAM, and I couldn't resist to show that, which is M51 here in CO 120, with the plateau de Bure, simply to show you that with the millimeter emission, you really have complementary information as compared to the optical, where you trace here the regions where the stars will be born. So what will ALMA do? It will range over all series of topics of modern astronomy, from the cosmic origins to the formation of galaxies billions of years ago, formation of stars, formation of planets around disks, and in disk, and then of course the chemistry of clouds and the new solar systems. This is the way that ALMA will do it. I will perhaps skip this slide. So let me now finish in the last minutes I have for this talk with a few examples of the transformational science that ALMA is doing as today. You have to be forewarned here that all the results that I show have been obtained with a limited amount of antennas, typically around 20 or so. And so you can imagine with the doubling of the number of antennas, the leap in sensitivity and also efficiency and quality of the data. So let me start with the solar system. This is comet Ison that ALMA observed. It was a big excitement here because it was quite a wonderful object. And there were many observations which were foreseen and planned at pre-perihelion, perihelion, and post-perihelion. So unfortunately, comets are very nice to have like cats, big tails, fluffy, but also like cats that do exactly as they wish. And when it went through the sun, it just evaporated and disappeared from view. So ALMA unfortunately observed the pre-perihelion time and got very nice data. Those are two examples of spectral line results. It's a paper by, I'll show it later here, where you see the signal to noise of the results, the HCN and the HNC with signal to noise above thousands or so. Those are the images. It's really a 3D spectral survey. And as you see, the HCN is very concentrated on the nucleus, whereas the HNC is the result of active chemistry and a coma with ejections and outflows. What is also remarkable in those data is this data set is about half an hour or so of observations. The other big topic of ALMA are the protoplanetary disks, and here are results of Keplerian rotations. To the left, disk winds, and also the famous CO snow line where the molecules are frozen in the center and stuck on the dust in the form of ice. The transitional disk and the gas flows and dust evolution. This was one of the surprises of the first ALMA results, where you see that the dust distribution is very asymmetrical, where the biggest dust grains tend to be located in particular regions of the disks. And the idea here is that those loci are the places where planets will be formed. This was a surprise. It was not exactly predicted by models, but this seems to be the case generally now in all the disks which have been measured with ALMA. Debris disk is another major topic of ALMA. You have everybody has seen the Follamont example here to the left, but let me show you a recent result obtained on Beta Pictoris, where it was the first measurement of the CO emission in its disk. Here you see an image showing the dust emission, which is very symmetrical in this debris disk. But if you look at the CO, it is completely asymmetrical. And one of the ideas is that the CO is released through collisions of dust and grains, and that the lifespan of that pocket of emission of CO is something like 100 years or so. This is a paper by Bill Dent, appeared in Science this year. On star formation, of course, ALMA will play a big role in understanding the physics of when a star is born. Just to enhance this is a view obtained in the optical with the VLT, and if you look at ALMA, here that's the result of the CO outflow of this young object, H4746. And as you know, you really see deep into the cloud, and you have an exquisite detail of how the outflow is structured. Astrochemistry is another big topic, and this was a result published last year with the detection of glycoaldehyde, so a form of sugar, which plays an important role in prebiotic evolution. The evolved stars is also a topic which I think ALMA will revolutionize, and this was an old example, but to the right there's another one from the right of rectangle. And I think with the exquisite sensitivity of ALMA, there will be lots of renewed interest in the late stages of stellar evolution. So this is the example of a sort of solar mass type star, and this is the results on a supernova, so a much more massive star. Those are the spectra and the detection of molecular gas. But I think the remarkable result of this year was the detection of dust in SN 1987A with the estimate of about a quarter of a solar mass of dust, which was formed over the last 10 years or so in this young supernova remnant. Results obtained at 3-kilometer baselines, also in an evolved star here. The number of antennas is 16 to 20, and the maximum baseline is 3 kilometers. So let me show you a few examples. So those observations were done on the water laser emission at 325 gigahertz. You see here to the right, to the left, the continuum in contours, and superimpose the water emission. Since we do a band, and it's a wide band, we pick up also other molecules, and to the right, the richness of ALMA, where you see a molecule. I don't know which one it is, but it's a completely different distribution. This is an observation at the highest resolution with 650 gigahertz and a resolution of 0.1 times 0.06 arc seconds. So I think that is better than the Hubble Space Telescope. And this was the science verification. You see that you start to really see details in the water emission in the center of this star. Let me now go in the last minute or so to extragalactic work. There, ALMA, of course, plays an essential role. This is an example, which is a beautiful example of a measurement of the suppression of star formation in an active galactic nuclei because of the molecular outflow in the center. And the starburst-driven winds limits the star formation activity. I think it's the first time that this is really measured. Another nice example is the measurement around the black hole of NGC 1433, where you really see the spiral structure where the mass the matter is spiraling down to the black hole. And also there was a discovery of an ejection of a jet here, which was a surprise to the authors who published that paper. Let me now finish to the extragalactic work with a couple of examples. This is a recent published paper with, I think, the first detection ever of molecular gas in a gamma-ray burst for two dusty galaxies at redshifts of 0.4 and 0.8. And what is remarkable here is that the ratio of molecular gas to dust is very low. And one of the ideas is that the gas has been dissipated by the newly formed massive stars. This is an example of what ALMA can do by resolving the carbon plus line, which is one of the major coolants of the interstellar medium, in a system at a redshift of 4.7. You see here the different channel maps of C+, and it's clearly a rotating disk which is extended and with a very high turbulence, so that essentially it's an unstable disk. It is an example of a Venetian galaxy undergoing its first major burst of star formation. Finally, the results which were published last year of the follow-up of the South Pole Telescope sources, which are lensed sources, and you see to the top here images. The red is the ALMA observations of the distortion due to gravitational amplification of the emission by the background source. Those are better images of here. There were 26 sources which were observed. They were all resolved, and 10 of the sources had redshift greater than 4. It's a number of dusty starburst galaxies at high redshift, and it's much greater than previously thought. Those are the spectra which enabled to do the measurement of the redshift. Those of you who have done optical spectroscopy know how difficult it was in the past to do such measurements. What is remarkable here is that each of these spectrum is less than 10 minutes of observing time with about 16 antennas. So it really shows you that ALMA in the future will be a real machine to probe the high Z universe when the universe was very young. And in my opinion, we are just at the entrance of a new era in millimeter, submillimeter astronomy. In the coming months and years, we'll see with the full operating ALMA a flurry of data, I think, covering from the solar system, star formations, galaxies, our own galaxy, and the high Z universe, including also, hopefully, surprises that will probably stun the astronomical community. So let me now thank everybody who has contributed to this project. This is a picture showing everybody. You don't recognize it, of course. And let me finish by thanking you.